Hi, my name is Jordan Donovan. I worked on this project with Aljan Mertin, um, and our research question that we were trying to answer with the cellular automata was, how can pursuing novelty affect discovery? So um, to answer this question, we designed two automata. One is a novelty automata, and one is a trendy automata. The novelty automata has two binary states, occupied or vacant. Cells neighborhood is a Moore neighborhood with a radius of 1. The boundary is periodic or torus. Um, and our rule set for novelty automata was, if a cell is on, turn it off, and if a cell is off, turn it on if it is connected, if it has at least one neighbor that is turned on, but has less than or equal to the average number of neighbors for all cells that have at least one neighbor. So we went through and looked at all the cells, and if they had a neighbor, we added up the amount of neighbors, and then we divided by the number of cells that had neighbors. So the average number of neighbors for all cells that have at least one neighbor. And that's what we defined as novel. And that kind of defines the how this novelty automata works is that turning on the cells that don't have a lot of neighbors. It's pursuing a direction that doesn't have a lot of attention. So the trendy automata, for comparison, has the same binary states, the same neighborhood, the same boundary. The rule set is, if a cell is on, turn it off. If it's not trendy, so this is the exact opposite of novelty. If turn it off if it has if it's connected but has less than or equal to the average number of neighbors for all cells having at least one neighbor. And then if a cell is on, we also want to turn it off if it's trendy with a very low stochastic probability. And the reason we do this is because we have another rule in here, the last rule, that says if a cell is off, turn it on with if it has at least one neighbor but has less than or equal to the average number of neighbors for all cells having at least one neighbor. So even if it's not trendy, we have a low % chance of turning that cell on. And we had to do that because if we don't, then this automata doesn't explore outside of its initial initialization area. So it doesn't ever explore any other area if we don't do that. It just collapses and never explores anything. But this gives it at least some bit of chance to explore outside of its other rules. And so if a cell is off, turn it on if it is trendy, if the average number of neighbors for all cells having at least one neighbor, if it has more than those number of neighbors. So we use 1/8 as the stochastic probability for the for these two rules that are less likely. We use 1/8 because that's how many neighbors. It has 8 neighbors in a Moore neighborhood, but you could use different values and that might change the outcome. So our experiments involved two different sizes of grids. We used a 20 by 20 grid and a 200 by 200 grid. And we did a comparison of a random initialization where we turn on 80% of the cells in the grid. And then we also did a comparison on a cluster initialization where we only turn on a small cluster of cells in the grid with a 50% chance of them being on or off within that cluster. And you can see kind of an example of both to the right here. So our results are interesting. For the random initialization, the novelty automata for discovery of cells, so this is like finding cells in the grid over time. The novelty automata discovers all of the cells in the grid in both the 20 by 20 and the 200 by 200 grid sizes really quickly. Before 20 iterations on either, it has discovered all of the cells, whereas the trendy automata doesn't discover all of the cells until iteration 60 for the 20 by 20 grid. And even though it looks like the trendy automata discovers all of the cells in the 200 by 200 grid, it doesn't. It gets very close, but it doesn't actually ever discover all of the cells in the grid, which is interesting because we already gave it 80% of the cells with just the random initialization turning on 80% of the cells in the grid. So it started at 80% and it still couldn't make it to 100%. We see under diversity, we would expect novelty to be higher in these, and in the 20 by 20 grid it is higher, but the Trinity automata does maintain some diversity. And the diversity metric is standard deviation on both axes of the grid. And then in the 200 by 200 grid, we see that diversity starts off kind of high with a random initialization, and then it drops drastically down to less than 20% diversity, and we see that novelty maintains above a 40% in both cases, 20 by 20 grid and the 200 by 200 grid. And so the cells that are turned on over time, we see that in the 20 by 20 grid, both novelty and trendy kind of stay after iteration about 20, they stay at about 35% of cells turned on in the grid. And then in the 200 by 200 grid, the trendy automata kind of collapses into these clusters or trends and doesn't really have a lot of cells turned on after that. And it's less than 10% at the 600 iteration. Whereas the cells for novelty and pursuing novelty are at 35% throughout the entire run. So for cluster initialization, we see something similar in a lot of these graphs. The trendy automata never actually gets to 100% discovery in either one of the grids, and novelty again discovers all of the cells very quickly. Very similar for diversity, except that the trendy automata in the 200 by 200 grid doesn't start with very much diversity, so it just stays below 10% the entire time. And then the number of cells turned on looks very similar on the 20 by 20 grid. And then the 200 by 200 grid, the trendy automata never really explores much because it is following trends, and the trends are within a very localized area, and so it doesn't get very far, or doesn't have very many cells turned on. So the results of the final frames for each of these experiments is represented here on the random initialization on the left and the cluster initialization on the right. We see that I think the more interesting case is the 200 by 200 grid. You can definitely see the same kind of things in the 20 by 20 grid, but I think it's much better visualized in the bottom grids. And so like in random and cluster initialization, it looks like novelty just continually explores the space that it's given. Even at the 600th iteration, it's still exploring the entire space. And then we can see that the cluster and the random initialization for the trendy automata both collapse into these clusters, and that makes sense. It's following the trends, and it never actually leaves the initial cluster in the cluster initialization, and then in the random initialization it collapses into these more focused areas. And eventually those would go away entirely, whereas if you were to have novelty search on a larger time scale or in a larger grid scale, it's going to explore the entire space and continue exploring that space for forever, from what I can gather here. So this was just kind of a representation of an idea that we had about how novelty can affect discovery in different areas, applied to research or life in general, just how novelty differs from following the trends. But again, this is kind of just one take on it. The rules here could be changed, and you could come up with completely different results. So this is just our kind of take on it and our experiments. So I hope you enjoyed, and that's the end of this video.